Yeah, he's okay. I didn't even look at that.
All right, a ball's launched. We'll take off where we left off. Pick up where we left off. We already did this one, didn't we?
No, we're done. We're on the
We did this.
plane.
We're on the
We're on-
evil one.
We're on the
No,
eve.
we're on the plane one.
Okay, we did this one also, didn't we? Or we did
That's
this
for
one.
homework.
We're doing it for homework.
Oh, did you do this one for homework?
Yeah.
But it's the same one from the other day.
It's like I talked about the other day. It's the exact same problem as launching something horizontally. So you should get the exact same answer as what you did before. But you always you take it back to, okay, at what point do I need to drop this so it lands where I need to land? Like I said, that's what happened back in World War II a lot, in Korea and Vietnam. We're going to talk about, there we go, Evel Knievel. Evel Knievel used to be a daredevil. Let me pull this over.
Oh my.
We'll show his infamous ride.
A jump and crash.
Yes.
Oh, jeez.
Okay, this is Caesar's Palace out in Las Vegas. Go ahead, cut them both, hit them both, turn them off. You're fine. You can see. Okay. He flew over Caesar's Palace, but it did not end up well for him. Okay. He basically turned into a crash test dummy as he landed, and they said he pretty much broke every bone in his body.
Did he die?
No, he did not. Robbie Knievel is his. There's other ones here.
Jumping?
Evel Knievel's real name.
That's what he called himself. There was many of them that did make it, and there's many of them he did not make it, or not many of them. The one main one he did not make. Yeah.
Were they parked like this way?
No, not lengthwise. They am side by side. That's why they're just looking small. Okay, how fast does Evel Knievel have to be going to clear the 14 buses? So now we are looking at, this is the engineering problem that they had to figure out, because if he was not going fast enough, the obvious conclusion to the jump would not be very good. He's not going fast enough, he would hit that corner or hit the bus. If he's going too fast, then he may land all the way down here or even down here and miss the ramp totally, which is not good, because as he is going, he's going to be going at an angle coming down to try to hit the ramp here. So he's trying to hit the ramp, and then he has his front wheel up a little bit, but he's trying to get the correct angle so it's not a hit here and then a slam down with the front wheel. Doesn't want that either. Okay, so he has to be able to judge in regards to how fast he's going where he hits. And obviously, if he hits down here, that's not going to be a good thing either, because he's expecting a downslope when he hits. We have 14 buses, has a measure or a length of 40 feet or 40.54 meters. Almost, not quite half a football field. We want to calculate how fast he needs to be going as he leaves the ramp. We need to find what is this initial velocity. Okay, that's what we're trying to calculate. The heights of each one of these ramps are 3.848 meters. So if we start taking a look, we have two-dimensional motion here. We have vertical, we have horizontal. We're trying to calculate initial velocity, so we don't know anything about that. We don't know anything about final. Acceleration, we still have acceleration in a vertical sense, because things will launch and things will fall. This time, though, our projectile that we are launching is a person on a motorcycle. We'll calculate Jack's speed that he has to get for his unicycle to go over the 14 buses. We don't know anything about time, but we do know displacement. In a vertical sense, what's our displacement? Zero. Because we are launching our projectile 3.48 meters above the ground, and we're hopefully landing what we had to clear is 3.48 meters above the ground. Displacement horizontal, 4.54 meters. But what we need to calculate is we need to calculate our initial velocity. Well, we have two components to this initial velocity. We have a vertical Vy, and we have a horizontal Vx. We have two components there that we need to calculate. We know nothing about the time. We know nothing about final initial. So we need to start looking at components here. We know acceleration horizontally is 0. We know displacement is 40.54. So we're sort of, if we look at our equations, can we find anything? Okay, first two we need to know V final and also V initial. We don't know either of those. So that gives us a problem because we don't know two of those quantities. We know displacement is V initial t plus 1/2 at squared, but we need time for the last one. I know acceleration, I know displacement. We know this, but I don't know time, and I don't know initial velocity. So we have problems with that too, don't we? So let's take a look at another aspect of this. We're just going to call this V here. What I do know is I know those two values there. Which, if I take a look, we also have a triangle that's a ramp. And this triangle is, it looks like, hopefully we built this to be a right triangle. And if we have a right triangle, there we go. If we have a right triangle, we can always go back and look at something that is associated with our good old buddy Pythagoras. Can we find this angle here? Can we find this angle? Which one of our trig ratios relates this angle to these two sides? Tangent. So we know the tangent of theta is equal to 3.48 over 22.55. What's our angle? That 8.7. So we have 8.7 degrees. 8.8, is that better? How about if we go 2 decimal places? 8.77 degrees. So we have, this is 8.77. So this angle up here, the launch angle, has to be 8.77 degrees also. We need to launch them going 8.77 degrees, which our Vy then would be V sine of 8.77, and our Vx would be V cosine 8.77. So now that gives me an initial velocity in terms of the actual velocity that we are leaving. So that gives us something to work with the V initial. And if I take a look, I know something about displacement here. I know something about acceleration. So I know displacement and acceleration. And this is void anything with a final velocity. So if I start looking at some aspects of this, in the vertical world, my displacement is equal to V initial t plus 1/2 AT squared. My displacement initially, or I'm sorry, in the vertical world is 0. My velocity is V sine of 8.77 times this value of t plus 1/2 negative 9.81 t squared. In the horizontal sense, horizontally we have 40.54 meters is equal to V cosine of 8.77 times t. And I don't have any acceleration. So this nicely goes away to nothing. So we have 40.54 is equal to V cosine 8.77 times t. Over here, we have 0 is equal to V sine of 8.77 t minus or plus a negative 4.905 t squared. Which now leads us to the idea of algebraic systems of equations. I have two equations. I have two unknowns. I have velocity and I have time. And this velocity v, by using our trig functions, is that initial launch velocity. This is my v here. This is v sine, and this is v cosine, which now allows me to use my algebraic skills. Over here, it does not matter which one to solve for because I have t and t squared and I have v. I would tend to probably solve for v over here, so I don't have to square quantities. So if I solve for v over here, this would be 40.54 divided by t times the cosine of 8.77. I just moved the t out in front. Which gives me a quantity, because this v and this v, since we broke it down to its components, this is the magnitude that's going to be exactly the same. It's the magnitude of v horizontal and v vertical. We can then take and substitute in. So we have 40.54 divided by t cosine of 8.77 times sine of 8.77 t, and this is equal to 0. Minus 4.905 t squared. Now, if I take a look at my first term on the right, can we cancel something? That's sine and cosine. If we wanted to, we can make sine of 8.77 over cosine of 8.77. That would equal the tangent of 8.77 if we wanted to. But if we take a look at the t's, our time here, I have over 1, and this is on the bottom. This is still all multiplication, so these times cancel out. So we have 0 is equal to 40.54 sine of 8.77 divided by cosine of 8.77. And if we wanted to, we can really go all in and say this is equal to the tangent of 8.77 if we wanted to. Is equal to negative 4.905 t squared, or plus negative 4.905 t squared. So what we now have is just one equation with one variable, and that's time. So we can add this to the other side to make it positive. If you want to, you can. If you don't want to, it's fine. To solve for time, what do we have to do now? We have t, we can divide by 4.905. And then we have a t squared. To get rid of the square, we have to square root. And once again, if you take 40.54 times the sine of 8.77 divided by cosine of 8.77, that is fine. And then divide by the 4.905, you'll get the same answer. It just looks fancier. It's, you know, I know my trig stuff. Pythagoras would smile. How long does it take him to fly over the 14 buses? How'd we get? 1.275 seconds. Yes, no, maybe so. So now we can calculate a velocity, and you can go into either one here, either one of these equations, because they'll give me my velocity, v. If I go up to this one right here, because this is a little bit easier, I've already solved for v. v is equal to 40.54 divided by time 1.275. Divided by a cosine of 8.77. Gracias. Do you need a pass?
No.
You need to study hard. So what's his velocity have to be? $31 point what? 31.42 meters per second. That's no, maybe so. Todd, you don't look like you quite agree.
I got 32.17.
32 point what?
17.
Is that better, Todd? All right. So that has to be his final velocity or initial velocity upon launch. Now, if you convert that into miles per hour, let's see, meters per second, 32.17. 32.17, basically about 72 miles per hour. And once again, if you increase the length that he is jumping, that increases. And if you look at a motorcycle, I mean, you're going 14 buses, going up to 72 miles per hour, they're sort of sometimes limited in regards to their space that they have to get up to that, so they have to accelerate, quickly to be able to get to that point. And if you don't quite get to that point, what they started to do, and you saw that on the one thing, they started to put a little flapper there on the landing ramp. So if it did come up a little bit short, their calculations were a little off, or the wind was a little bit different, or there's also some acceleration or deceleration by if you're revving your tires, spinning your tires, and you're in the air, that's going to create a negative acceleration or slow you down a little bit because you're spinning your tires, and you could get a little bit of a adverse effect to it. It slows you down a little bit. So they started to add, once again, this little flap here, if they came up a little short, that they could at least land on here. So they're not going straight into a ridiculousness moment and just hitting straight into the wedge there. Okay. And they're just sticking there. at least they have a little chance of survival. At that point, they land on the flat and then they continue to go downwards. Used to be a big thing. This here used to be a huge thing, to be able to jump over X number of items. I mean, it used to go to television and used to be a big thing on television. Wide World of Sports used to televise this. You know, the thrill seeking that you had. I remember, oh gosh, it was maybe about 15 years ago. Red Bull had something on New Year's Eve that launched somebody up and they landed on something. I have to look it up now. We will stop there today. Tomorrow, once again, I'll just have some problems for you guys you can work on with the sub. And feel free to be able to talk. And now I'm going to look up Red Bull.
Jack, you're the one who's-
2008. Robbie Madison's.